Can you hear me? Okay, we are going to start in 1 minute. Okay, let's get started. So it's my first time to use the YouTube Live. Let's try to see whether we can make the makeup class successfully. And hope you already get home safely. So it is still snowing now, right? Okay, so today we will continue to introduce the hypothesis testing, chapter 8. And then let's see whether or not we can finish this chapter and talk a little bit about the chapter 9, which is the t-test. So on Monday, we introduced the logic of the hypothesis testing. let's get a short review first. So a hypothesis test is a statistical method that used to sample data to evaluate a hypothesis about a population. So it's related to the inferential stats. We got some sample data, and then we want to use the data to test whether or not our sample data support or not support our hypothesis about a population. So we have 4 steps for the hypothesis testing. First step is to state a hypothesis about the population, and then we make a prediction about the statistics in the specific sample. So after we have the hypothesis and after we make the prediction, then we collect some data by random sampling some individuals from the sample after treatment. And then we compute the statistic. From this sample, we compare the obtained sample data with our prediction. If they're consistent, then we have evidence to support our hypothesis. If they're not consistent, we have to reject our hypothesis. So we have 2 major assumptions. The first one is that population is known before treatment, means we know its mean and the standard deviation, the mu and the sigma. But the population after treatment is unknown, and the treatment effect just can be simply considered as just to add a constant amount or subtract a constant amount from each individual score. So the mean will be increased just as the old mean plus a constant or minus a constant, and the standard deviations is not changed. Right. And so the hypothesis consists of 2 parts. The first one is the non-hypothesis. So the non-hypothesis states there's no effect, no change, or no relationship. Means the population mean after treatment is equals to the population mean before the treatment. And the alternative hypothesis states we do have an effect as the population mean after treatment will be not equals to the population before treatment. After we state a hypothesis, and then we have to set a criteria for decision. So we call the criteria as alpha value. Alpha value, or the level of significance, which is a probability value, right? To define how unlikely a sample will be obtained. So we have a keyword called critical region. Critical region defines the extreme sample value. They are very unlikely. And if we looking at this figure, so this is the distribution of our population scores before treatment, right? And the horizontal line is the alpha value, and the area in red we call it as the critical region, because the critical region is just in a small proportion of the distribution. So it's very unlikely a sample will fail in these regions, the red regions. And we call the lines as the boundary of the critical region, right? So we usually define the identified boundary as an z-score corresponding to the alpha value. And so In last chapter, we learned if we know a probability, right, and we know the data is in the normal distribution, we can find the corresponding z-score of this probability value using the uni-normal table in the appendix B.1. And so the logic is, if the sample mean fell into the critical region, means the region in red, means it's very unlikely, right? We can get this sample. So we reject the non-hypothesis. If the sample mean are not in the critical region, means in the white area, and then it's the high probability we can get this sample when we are doing randomly sample from the population without treatment, before treatment. So then we cannot reject the non-hypothesis, right? Means if, right. And usually we have this kind of predetermined alpha value, for example, at alpha equals to 0.05, which corresponding to the z equals to plus or minus 1.96. So here the z-score is the boundary of the critical area. So alpha equals to 0.05 means the probability just 5%, we can get a sample with the mean fair in these regions. If we are randomly assembling a sample from the population before treatment, so means is very unlikely. Then means we have the evidence to reject the non-hypothesis. And then at alpha level, we can also use 0.01, and with a bigger z-score, means for a bigger distance from the mean to the boundary of the critical region. So the 0.01 is more liberal, more conservative than the alpha equals to 0.05, means it's more unlikely we can randomly find a sample with the mean fell into this smaller region. So we can also use the alpha value as 0.01, which is even more conservative. And after we determine the critical regions, then we can work on the sample, right? The sample means the data we get. So we can calculate the sample mean, which is the M, and then we calculate the z-score, right? That identify where our sample means is located in the hypothesis size distribution. Just use the sample mean minus the population mean divide by the standard error of the mean. Here we divide by the standard error because we are dealing with the sample mean, the distribution of sample mean, not the distribution of scores. So after we have the t-value, this t-value of the sample mean, and then we can make a decision by comparing this t-value to the boundary of the critical region. So if the sample mean are located in the critical region, means if you still remember, means the region is in red, and then we are going to reject the non-hypothesis. Means we reject hypothesis which said there's no effect. So means we interfered that may be an effect. If the sample data are not in the critical region, right, means the sample data are in the wide area, so we cannot reject the unknown hypothesis, means we can just have to accept the non-hypothesis that which said there's no effect. So last week we showed this sample, right? The sample in the red frame, we found these. So we have the same criteria for the significant level, but with different sample mean. The same criteria and the same population distribution, but with different sample mean. Right? This one is bigger. This one is smaller. So the boundary is determined by the alpha value. So the boundary of the critical region are the same, right, in these two examples. And then we compute the z-score of the sample mean. So we in this sample, the sample in the red box, the z-score equals to 0.25, and then we use this number to compare with the boundary, right? So if the z-score is greater than the upper boundary, means the positive boundary, or the z-score is smaller than the lower boundary, means the negative boundary, and then we say it's located, the sample data is located in the critical region. So we reject the non-hypothesis. So we said we do have an effect, right? But here, you see the z-score is 0.075. So it's between two boundaries, the positive and negative boundaries. So it's not in the critical region. And then we have to accept the non-hypothesis. So in this example, we said we don't have any treatment effect. And then let's do a practice, right? That's what we covered last Monday. And then let's do a practice. So in this practice, the normal population sample has a mean of mu equals to 40, and the standard deviation of sigma equals to 8. So this is the sample before treatment, right? This is sample before treatment. And then after a treatment, this is a population before the treatment, population before the treatment. And after the treatment, we randomly sample a group of 16 individuals from the population, and the sample mean is found to be as m equals to 45. So this is the statistics of the sample data, right? And then we are asking whether or not we have sufficient data to reject the non-hypothesis, and then to conclude there is a significant treatment effect with an alpha value as 0.05. So here we have the criteria of the decision, right? And then let's get started. The first step, we state the hypothesis, right? The hypothesis H0 means we don't have any effect. So which means, enlarge this one a little bit. Right? Which means the mu after treatment equals to mu no treatment. Right? The mu no treatment is 40 in this sample, in this example. Right? And here we have our non-hypothesis. And then the corresponding alternative hypothesis, which is H1, will be just replace the equal sign to the unequal sign. Means we do have a treatment effect. So the population mean after treatment will be significantly different from the population mean before treatment. So we finish our first step. But if you have any question, you can type in your question. And then we set the criteria for the decision. So here we know the significant level is alpha equals to 0.05. And then we are going to find what's the boundary of the critical region, right? So in this slide, I just tell you if the alpha equals to 0.05, the boundary will be z equals to plus or minus 1.96. So means we have boundary, means the critical region here will be any z greater than positive 1.96 or z smaller than negative 1.96, right? Here we define our critical region based on our significant level. And then we compute the sample statistics. Here first, because we are dealing with the distribution of the sample mean, right? So we have to compute the sigma m, which is the standard error first. So here's the formula: sigma m equals to sigma divided by the square root of n. So the sigma is 8, and then divide by the square root of n, which is 16. So which equals to 8 divided by 4, and that is 2. And then we compute the z of the sample mean. So use this formula. The sample mean here, m equals to 45, minus the mu here equals to 40, divided by the sigma m, which is 2. So it's 2.5, right? Positive 2.5. And then we have the z-score. So the last step, we make the decision. So the z-score equals to z. No. What did I do? Z equals to 2.5, sorry. And then we compare the z with our boundary, right? Which is greater than positive 1.96, means in the critical region, right? So we make the decision, we reject the non-hypothesis. And then, not here. Therefore, the answer will be, right? We do have sufficient evidence to reject the non-hypothesis and conclude that there is a significant treatment effect So that's our answer. And then we solve this question. So any question? Okay, so if you don't have any question, let's do some learning check. Right? It's just a similar question. Right. So we are just going to test whether or not the treatment has no effect. So here we know the population mean and the population standard deviation before treatment, and we know the sample mean after treatment. So we follow the same strategy, right? The non-hypothesis means the treatment do not have an effect, means that the mu after treatment equals to the mu before treatment, means the mu after treatment equals to 40. And then we use the significant level, the same significant level, for example, alpha equals 2.05, which is the most liberal significant level. We cannot use any significant level more liberal than this one, usually. And then we know our critical region. So we just need to redo the computation of sample statistic. The same thing. So the sigma mean equals to 12 divided by square root of 16, which is 3. And z equals to divided by 3, which is plus 0.67. So, and then we know, make the decision by compare the z to the boundary, right? So we know this value is between two boundaries. Means it's not in the critical region. So means accept the mean, right? Accept the none. So let's check which one is our choice. Is the extreme, it's an extreme value and it's very unlikely, so that's not true. And then B is much the same as the sample and would be obtained if the treatment has no effect. Yes, that's what we found, right? So C is not correct because it's notably larger. Notably larger means we do have a significant treatment. In fact, this is not true. There's no way to compare the sample with the population. So we have a way to compare, so this is not true. So the answer will be B, this one, B. Right. Just follow the similar steps, right? Let's do the next one, the next learning track. Our researchers select a sample of 12 individuals from the normal population. We know the mu and sigma, and a treatment is administered. So what's the non-hypothesis? Here we are asking about the non-hypothesis. So means we know the non-hypothesis is the treatment does not have an effect, right? So it's about the mu. It's not about the sample mean. So B and C, they are not correct, right? It should be either A or B because we are talking about the mu. So non-hypothesis means we don't have any effect. So the mu should be equals to the mu before treatment. So the best choice is A. A. This is the definition of the non-hypothesis. Right. And what is the correct decision in the hypothesis testing if the data produces z-score that is in the critical region? Right. If in the critical region, here we know we reject the num. We reject the num. It's the step 4 of hypothesis testing. So A is the correct choice. Right. Let's continue. Let's introduce what's the uncertainty and errors in hypothesis testing. Right, it's a new topic. So we have two types of errors, which the first one we call type 1 error, which is also called as the false positive. What is type 1 error? So a type 1 error occurs when a researcher rejects a non-hypothesis that is actually true. So non-hypothesis means we don't have a hypothesis that we hypothesize that there's no effect. But if there is an effect, we just cannot find evidence to support it by chance, right? And then we have a type 1 error. So here is an example of type 1 error. So if a man asks the doctor whether or not I'm pregnant, and then the doctor said, yes, you are. Yes, you no. Oh, the type 1 hypothesis. Sorry, so we reject the non-hypothesis if there's non-hypothesis true means there's no effect, but we said there's any effect. Sorry, I made a mistake, right? So type 1 error is when there's no effect, but by chance we got an extreme example. So we said we have evidence to reject the non-hypothesis. So here, if a man asks the doctor whether or not I'm pregnant, and the doctor said, yes, you are pregnant, but it's impossible, right? So means we reject a non-hypothesis that somebody is not pregnant, no effect, and which is actually true. But by a mistake, we said we reject the num. So he said that he has a pregnant. So means we have the positive effect, but the positive effect is false. It's not true. So we also call it false positive. And type 2 error is the false negative effect. Means we fail to reject the non-hypothesis. That's already, it's really false. Means we do have an effect, but we didn't get any evidence and enough evidence to reject the none. So here is another example. So this woman asked daughter whether or not I'm pregnant. So obviously she's pregnant, but doctor just tell her you are not pregnant. So not pregnant is a negative effect, right? But the negative effect is false. It's not true. So it's a false negative effect. The probability of type 1 error is determined by the alpha value, and just the same as the alpha level. So if the alpha level is 0.05, means the probability of type 1 error is just 5%. It's the probability of obtaining an extreme non-representative sample. But the probability type 2 error, right? So the type 2 error, the probability of type 2 error is a little bit complicated. It's impossible to determine a single exact probability for a type 2 errors. Instead, the probability of type 2 error depends on a variety of factors, and therefore it is a function, right, rather than a specific number. So let's focus on the probability of type 1 error first, because the type 2 error is too complicated. Right? Any question about the type 1 and type 2 error? Okay, so type 1 error, right, means, for example, last time we have an example like this. So we just have an example like this, right? In the normal population, we administrate a treatment, right? And the sample mean, which is something, right? It's not 0.4, it's 45. It's 45, right? It's 45. And but so if you're considering a distribution with normal distribution with the mean as 40 and standard deviation as 8, by chance, right? If we are doing the random sampling, by chance we can get an extreme sample, right? For which mean is 45. So here, the 45, we just say is very unlikely. We just have 5% of probability we can have this kind of sample without treatment. It's very unlikely, but very unlikely does not mean impossible, right? It's still possible. So we have 5% of probability to get this extreme sample if there's not the treatment has no effect. So the 5% is the probability of type 1 error. And type 2 error is, for example, if the standard deviation is bigger and we compute the z is not in the critical region in this sample, but we do have an effect. We do have an effect. Just by chance, we got a sample with its mean close to the population mean before treatment. So that's the type 2 error, but the probability is hard to determine. Right, so the type 1 and type 2 error is not a mistake you made. It's not a mistake, right? It's just something something naturally. We have a probability you will get an error if you are doing random sampling. And for a statistical decision, right, there are 4 possible outcomes. The first one is if we do not have a treatment, if we have no effect, means that the non-hypothesis is true. We don't have any treatment effect. And then we said, but we said with our decision is we reject the none, means we said there it is an effect. So if there's no effect, but actually there's no effect, but we said yes, there it is an effect. So this situation is type 1 error, right? But if there's no effect, and then we fail to reject none, we also said yes, there's no effect. We said there's no effect. It's true, there's no effect, right? So our decision is consistent with the actual situation. So here we make the decision correctly. And another situation means it is an effect, but and then we also reject the none, means we also make a decision that yes, there it is an effect. So they are consistent. So we make the decision correctly. But if there it is an effect, but we fail to reject the none, means we say no, there's no effect. So they are not consistent. This situation is the type 2 error. So it's hard to memorize which one is type 1, which one is the type 2, but maybe this table will be helpful. Right. Okay, so the probability of type 1 and type 2 error is related to the alpha level. So the probability of type 1 error is determined by alpha level, right? So it's directly related, and the type 2 error is indirectly related to alpha level, which is complicated. And when we are going to select an alpha level, so we have to consider the trade-off between the risky of type 1 error and the probability of detecting a treatment effect, right? So if we use a liberal alpha level, we have a high risky of type 1 error, means there's no effect. Actually, there's no effect, but we said there it is an effect. So means we have high probability a sample will fail in the critical region. But if we choose a very conservative alpha level, for sure we have lower risky of type 1 error, means we have lower probability and extreme value sample will be obtained. But in this situation, right, it's very hard to detect a treatment effect. Only when the treatment effect is very significant, means the sample mean is very far from the sample mean of the sample after treatment is very far from the original population mean before treatment. So there's a trade-off. So how to select alpha value, right, is a big question in real research. We can start with a very relatively liberal alpha value, which is 0.05, and then we can try to see whether or not the result can still survive with a more conservative alpha value. But during the discourse, right, I will not ask you to select an alpha value. I will tell you what's the alpha value we are going to use to solve a certain question. Typically, we use 0.05, 0.01, or 0.001. Okay, let's do some learning check, right? When does a researcher risk a type 1 error? Here, we are asking about the definition of type 1 error. All right, so that's it. Type 1 error is the false positive. False positive means we reject the num, but it's not, but it's false, right? So we said when we reject num, but it's false. So when we reject num, when anytime we reject num, we risk a type 1 error. So the correct choice is A. Anytime we reject the null hypothesis, we risk a type 1 error. And in the hypothesis testing approach, we never reject H1, we just consider about the H0. So the next question asks you about the definition of type 2 error. Type 2 error is the false negative. False negative means we fail to reject a non-hypothesis. So it's not A, not B, fail to reject a non-hypothesis, but it's when the non-hypothesis is false, right? Okay, so fail to reject a false non-hypothesis, which is the definition of type 2 error. So the answer is C. C. And what is a likely outcome for a hypothesis test if a treatment has a very small effect? Very small effect, but we do have an effect, right? So, but if the treatment effect is very small, it's hard to detect, means we may fail to reject the non-hypothesis. We may fail to say there's no effect. So when we fail to reject the non-hypothesis, but then we do have an effect, means the non-hypothesis is false. So we fail to reject a false non-hypothesis, which is type 2 error. So the answer is B. Right. So if you have any question about these 3 questions, you just check the definition of type 1 and type 2 error. And let's continue to introduce the hypothesis testing. What's the factors that will influence a hypothesis testing? So we have 2 factors. One is the variability of scores. Right? If the variability of scores is bigger, is very big, means the so it will be hard to detect an effect, right? So the variability of the scores are not good for the hypothesis testing. We may fail to reject a non-hypothesis because if you consider about the z-score, right? Because we use the z-score to make the decision, right? The variability of scores when it's bigger means the standard error is big, right? If the standard error is big and the standard error of mean is big, if the standard error is big, means the z-score will be small. The smaller the z-score, the high probability it will be fair not in the critical region, means we will fail to reject the num. And another factor is the number of scores in the sample, right? So here we said the number of scores will affect the sigma m, which is the standard error of the mean. So a bigger n will produce a smaller sigma m. When the sigma m is small and the z-score will be big, right? So bigger sample size is good for the hypothesis testing. Larger sample size, higher probability to reject the H0. Okay. So if you don't remember which one is higher, which one is lower, you can just check the formula and follow what I just did. So the assumption for hypothesis testing with these scores, we have 4 assumptions. The first one is random sampling, right? So because the random sampling is the basic assumption of the probability in the normal distribution. And the second one is independent observations, means the individuals will not depend on one another. For example, right, when we are going to test a treatment effect in the campus, right, for example, the Queen's College, we cannot just make the observation in our class, right? We have to have some independent observations from different classes, because in this class we are observing something the same. And another important assumption is the the sigma value, means the standard error, the standard deviation of the population is unchanged by the treatment. So that's what we said, the treatment effect just to add a constant to each individual score. And the last assumption is the normal sampling distribution. So for these 4 assumptions, you just need to memorize what's the 4 assumptions. Okay. Let's do some learning check. So a researcher report a summary, the result of the hypothesis testing by stating Z equals to positive 2.13 with P smaller than 0.05. So which of the following is a correct interpretation of this report? Right here, we are asking about our decision and probability of errors. So so P equals to smaller than 0.05, right? It's the corresponding P value of the corresponding to the Z. So 0.05 means it's smaller than alpha. So if the P is smaller than alpha, means if this sample is it is in the critical region. If P is smaller than alpha, then means this sample it is in the critical region. So here we can reject the non-hypothesis. Okay, so for A and B, the non-hypothesis was rejected. And alpha is the probability of type 1 error, right? So we compare to the alpha, which is 0.05. This is the probability of type 1 error. So it's smaller than 0.05, so smaller than 0.05. Yes, then we can figure out the correct choice is A. Next one, which of the following is not assumption of the z-score hypothesis testing? So we have 4 assumptions. First one, observation must be independent. So it's not this one. It is assumption. The sigma will not change, right? It is assumption. And then random sampling, it is assumption. So the value of mu must be the same after treatment as it before the treatment. Here, the mu will not change is the non-hypothesis, right? It's not assumption of hypothesis testing. So B is the correct choice. If we have assumption, we always have assumption that we don't have an effect, then why we are going to we need to do a study? Right. Here we are asking about the factor that will influence this hypothesis testing. So originally we have a sample of 16 individuals, and from a population mean, we know the mu is 18 and the standard deviation is 5, right? And if we increase the standard deviation from 5 to 25, increase the standard deviation means we increase the variability of the data. So as we just said, the variability is not good for hypothesis testing. The higher variability, the lower probability, the lower probability we will reject none. Okay, so the lower probability we will reject none means increase the chance that sample will produce a z-score near 0, and increase the likelihood you will conclude the treatment has no effect. So D is the correct answer. So right, let me take a 5-minute break. If you have any question, you can type in. I will be back in 5 minutes. Okay, I'm back. So let's continue. Oof. Right. I will introduce the directional hypothesis, also called one-tailed hypothesis test. So a directional hypothesis test or one-tailed test is the hypothesis test specify either in an increase or decrease in the population mean as a treatment effect. For example, we said the treatment will significantly increase the population mean, or we have a hypothesis that the treatment will significantly decrease the population mean. So compared to the two-tailed hypothesis test, that's what we just introduced. We said the treatment, the population mean after treatment will be significantly different from the population before treatment. So the keyword here is increase or decrease for the one-tailed t-test. Different is for the two-tailed t-test. So for one-tailed t-test, we set the difference, right? For example, if you still remember the example we introduced on Monday, so whether or not we are going to test whether or not the widgets wearing in red will get more tips from men, right? So our hypothesis is the tips are not increased. Here we have the word increased in our hypothesis, are not increased. So we define the direction of the treatment effect. And then alternatively, our H1 is the tip are increased. Here the treatment has effect. So it are not increased means it doesn't change or it decreased. So both of this situation we call is not increased. For in the distribution, right? The critical region for a one-tailed test will be just entirely on one tail of the distribution. But for a two-tailed test, right? The critical region will be distributed into two parts. Each of them are on one tail of the distribution. Right, so two changes in the step-by-step hypothesis testing procedure. The step one is the directional prediction is incorporated to the statement of hypothesis testing. Here we said, so for example, here we said the treatment, the tip are increased. We have incorporated the word increased, and H1 is are not increased and are increased. So we incorporate the direction in the statement of hypothesis. And the step two, when we are determining the critical region, right? We are setting the critical region. So the critical region is located entirely in one tail of the distribution. Here, if the sample mean are in the critical region, and then we reject the none. So for one-tailed t-test, for alpha, significant level alpha equals 2.05, the boundary, not correct. If H0 is so mu mu, no treatment. But here, so if our prediction is, no, our hypothesis is, right? So the boundary depends on the direction of our hypothesis. So if our hypothesis is the treatment will have an increase of the population mean, right? And then the boundary is z equals to positive 165. So if our hypothesis is the treatment will decrease the population mean, right? And then we are assuming the critical region will be on the left side of the distribution. So the critical region of the boundary of the critical region is z equal to negative 1.65, right? And then if here the empirical effect and the hypothesis effect are in the same direction, a one-tailed t-test is more liberal than the two-tailed t-test, means we have a higher likelihood to reject the H0. Why? Because we combine. So here, because we have entirely the critical region on one side of the distribution, means if we do have the treatment effect as we predict, hypothesize, we have higher probability the sample mean will fail in these two regions compared to when the critical region are equally distributed to two sides of the distribution. So if you are going to find out what's the corresponding alpha, the z score corresponding to the alpha value for a one-tailed test, right? You need to use the boundary. Look up the unit normal table and column. I think this column B. Proportion in tail. Okay, let's do some learning check. So the one-tailed hypothesis testing is not that complicated. It's very simple. So here, a researcher is predicting that a treatment will increase the score if you see the word increase or decrease. So means we are talking about a one-tailed t-test, right? If this treatment is evaluating using a directional hypothesis testing, yes, it's a directional hypothesis testing, means it's one-tailed hypothesis testing. And then the critical region of the test, right? Increase, right? Increase. Consider about what's the increase. Critical region for the increase. So will be entirely in the right-hand tail of the distribution. Means we are assuming the population after treatment will have the mean greater than the original population mean, right? Greater, so it's on the right hand tail of the distribution. If we don't have the word increase, if it's different from a different scores, right? And then it's C. If it's decrease, and then it's B. But here, the correct answer is A. Correct answer is A. Okay, next question. A sample is selected from a population with a treatment of mu equals to 45, and a treatment is administered to the sample, right? So here we have keywords to decrease, a decrease in score. Keywords. Decrease means is a directional hypothesis testing, one-tailed. So here we ask about the non-hypothesis. Non-hypothesis, we are talking about the population mean. So it's not C, not D. And then a decrease, we don't have a decrease in the effect, means it will be equals or greater than the original mean. So here, equal or greater than the original mean is our non-hypothesis. So it's A. Right. Second question. A treatment to produce an increase, right? Keyword, increase in the population. And then the treatment is evaluating using one-tailed hypothesis testing, and the test produce Z equals to negative 1.65. Here, increase, right? In the first question, we said increase means the critical region were on the right hand of the distribution, means the boundary of the critical region should be Z equals to positive something, 1 point something, right? Or positive something. But here, the Z-score is negative. For sure, it's not in the critical region. So it's not in the critical region, then we fail to reject none, no matter what is the alpha value, because they are in different directions already. So the correct answer is C. We don't need to determine the alpha value, specific alpha value, because they are in different direction. We know we fail to reject none. Okay, let's introduce the last sim of this chapter. No, not the last sim, sorry. Effect size, a new concept called effect size. So in the hypothesis testing, right, we test whether or not we have a significant effect. But a significant effect can exist even when the effect is very small, but it's very stable, right? So when we are saying we have a significant effect, we don't know anything about the actual magnitude of that effect, whether or not it's big or small. And the significance is depends on our sample size, as what we just said, right? Sample size is one factor that affect the significance. So with a larger sample, we have higher probability to get a significant treatment effect. So means the statistical significance is depend on the sample size. A measure of the effect size is intended to provide a measurement of the absolute magnitude of a treatment effect, independent of the sample size. So it's another measurement. How to measure the sample size, right? Here we have an index called Cohen's-d. Cohen's-d can be computed as the mean difference divided by standard deviation of the mean. No, standard deviation, not standard deviation of the mean, sorry. Standard deviation of the population. Means the mu of population after treatment minus mu of population before the treatment and divide by the standard deviation of the population. So in the previous chapter, we know the sample mean is an unbiased measurement, estimation of the population mean. So the estimate, if we don't know the mean, the population mean after treatment, we can estimate the Cohen's-d. I estimated the effect size like this. The estimated Cohen's-d equals to the mean, sample mean of the treatment minus the population mean without treatment and divide by the sample standard deviation. Because none of these parameters are depend on the sample size, so the Cohen's-d, the effect size is independent with the sample size. And we typically report Cohen's-d as a positive number even when the formula produces a negative number. It's just a habit, no reason. How can we evaluate the effect size based on the magnitude of d, right? If d equals or smaller than 0.02, we said there is a small effect. If it's around 0.05, we said it's a medium effect. So if d equals to 0.8, we said it's a large effect. So in exam, right, you don't need to memorize this criteria. I will give you the criteria. I will give you this table, print it for the exam, and ask you what's our conclusion. So which kind of effect we obtain. Here is example, right? So in both example, we have significant difference. But here, these two distributions are more closer. This distribution distance are further. So here, effect size means the after treatment minus mean before treatment. So standard deviation, they are same. So here, the Cohen's-d is smaller. Here, the Cohen's-d is bigger. Both of them are significant, but here we have a bigger effect. Right, the effect size just can be considered as the distance between the dashed vertical line to the solid vertical line. Right, let's do some learning check. Which of the following is most likely to reject the norm, even if the treatment effect is very small? Very small means we have a very small effect size, right? So we said the hypothesis testing is influenced by two factors. One is the variability. Another one is the sample size. So a bigger sample and a small variability is good for rejecting a null hypothesis. So here, a large sample and a small value of sigma, we are more unlikely to reject none, even if the treatment is very small, if we have a large sample and a very small variability. So C is the correct choice. Next one, right? So we are going to compute the coherence D. Compute the coherence D. Let's do it. Compute the coherence D. Coherence D. Coherence D equals to M. Right? Treatment minus mu. No treatment. Parenthesis. Divide by sigma. So equals to 85 minus 80. Divide by sigma is 10. Here it's not the sigma m, it's sigma. So which is 0.5. We have our answer, it's D. Right. Here we are asking about the relationship between the standard deviation of the significant level and the relationship between standard deviation also of the coherence D, the effect size, right? So we just said higher standard deviation means higher variability is will decrease likelihood of rejecting the norm. That's what we just said. And then based on this equation, right, we said higher variability means the larger sigma here will produce a smaller coherence D. Smaller coherence D means a smaller effect, so will decrease the value. So it will decrease both likelihood to reject the norm and also decrease the effect size. So the correct answer is D. Next, so we finished the coherence D, the effect size. Right. This one is the last part of this chapter. We call the statistical power. So we talk a lot about the type 1 arrow, right? It's false positive, but we just talked a little bit about the type 2 arrow. So the statistic power is related to the type 2 arrow. Here we are going to estimate the probability of type 2 error means we correctly reject a false hypothesis. So type 2 error means we fail to reject a false hypothesis. Here the power is we correctly reject a false hypothesis. So the power equals to 1 minus beta. Beta is the probability of type 2 error. Right? But what's the beta? We know what's the alpha. It's determined by us, but we don't know what's the beta. So the beta depends on a lot of factors, and we need to follow this procedure to compute the alpha and then compute the beta. To compute the beta and then compute the power. Here is an example. So this is a two-tailed exam, right? So if the non-hypothesis, the original population is a normal population with the mean as 80 and the standard deviation as 10. So after treatment, right, we add 8 points as the treatment effect. So after treatment, the population mean is 88. And the standard deviation is not changed. This is our assumption of this hypothesis testing. The standard deviation will not change. So this is our sample after treatment. And then we are asking about what's the probability that we correctly reject a null hypothesis. So because it's a two-tailed test. So here the red size here. So these two vertical lines are the boundary of the critical area, right? And then if the sample mean are located in the critical area, we will reject the none. But here you said you think this one is the distribution of the population after the treatment, right? And we can see there's an overlap, right, between these two distributions. So if the sample mean here this line are located in the critical region, so we reject the none because we know it is an effect. So if we reject none here, means we correctly reject none. But the probability, but even if we have this kind of distribution, we still have a probability that the sample mean will fail in this region, here, the small triangle, right? Here. So the area under this small triangle is the probability of type 2 error. 1 minus the type 2 error is the area in red on the right side of the figure. So the proportion of the right area in the distribution of scores after treatment is the statistic power of the treatment. Right, it's hard to understand. If you don't understand now, you can go back to watch what I just said, and then try to understand why the regions in red is determining our power of the test. And then how can we I'm going to introduce how can we compute the power. So the first step is to determine the critical boundary of F in the original population before treatment. So we know the alpha, right? We compute the z-score corresponding to the alpha. So and then to compute the z-score, the x-score, the actual scores corresponding to the z. So here we have alpha as 0.05. We know the z-score should be positive and negative 1.96, right? And then first step, right? We know the alpha. Here's my alpha. Oh, it's here. Alpha equals to 0.05. That's what predetermined. So the boundary Z, because it's a two-tailed test, equals to 1.96. Okay. And then we can compute the score of the boundary. So X should be equal to mu plus C sigma m. So here we know the mu, the original mu, right, is 80 plus Z equals 1.96 times sigma m, which is 2. Then we can have as the, so this is the upper boundary, right, and the lower boundary, or this is our lower boundary, right? Something. So because we know the m is already greater than mu, so we just work on this upper boundary, right? And then we compute the z score corresponding to this boundary in the distribution after treatment is C equals to, right, mu minus mu minus mu divided by sigma m after treatment, right? So here mu is the x. We use 83.92 minus the mu after treatment, which is 88, divided by the sigma m, which is 2. So we know the new z equals to negative 2.6 206. So here is the z-score, right? We know this z-score in this distribution of this boundary. And then we are going to figure out what's the proportion of this area with the scores above this z-score. So we search the uninormal table for proportion in body z equals to 3.004, which is the power. And then we find our answer, right? If we know the power, we know the probability of type 2 error equals to 1 minus the power, and it's equals to 1 minus, which is 1.07. And then we know the probability of type 2 error, which is beta, right? So the beta is complicated, it's hard to compute. I would say it's optional for the exam. I will not ask you to compute the beta or the power in the exam because it's too complicated. But you need to understand what is the power. But I will ask you what is the power, right? You should know the power is related to the type 2 error. can be computed as 1 minus the beta, 1 minus the probability of type 2 error. Optional. So the power and effect, because both of them are determined by alpha, right? So they are related. In general, as the effect size increases, the probability of rejecting H0 also increases, which means the power of test increase. So they are in the same direction. And both effect size and power provide an indication of the strength or magnitude of the treatment effect beyond the significant level of the treatment. So because here we know the strength or magnitude, the significant level we just know whether or not it's significant. We don't know the effect whether or not it's big or whether it's big or small. So other factors that affect power, we have the sample size. A larger sample produces greater power for the hypothesis testing. And alpha level. So reducing alpha level for hypothesis test will reduce the power. And if the treatment effect is in the same direction of the prediction as our prediction, right? And then changing from a regular two-tailed t-test to one-tailed t-test increase the power of hypothesis testing. Right? You have to remember the factors that will affect the power. Okay, let's do some learning check, right? First, which of the following define the power of a hypothesis testing? Here we are asking about the definition. So what's the definition? The definition of power is just the probability to correctly reject a false non-hypothesis. So it's C. Okay. So what does increasing the sample size influence the likelihood of rejecting the non-hypothesis and the power of the test? We just said increased sample size is good for hypothesis testing, right? So it increases both the likelihood of rejecting the non-hypothesis and also increase the power. So it's A. A is correct answer. And how does an increase in value of sigma influence likelihood of rejecting the non-hypothesis and the power of hypothesis testing? Right? So we know the variability, big variability is not good for hypothesis testing. So both will increase. So the correct choice is B. Right. If you don't know why this one, you can check this slides. So let's have a short review. In this class, we introduce the logic and the 4-step procedure of hypothesis testing, right? You should follow the step-by-step approach. And we introduce what's the type 1 error and what's the type 2 error. So you need to understand the definition, right? And you need to understand the type 1 error is directly determined by the alpha value. And there are some other factors that will influence type 2 error and what's the factors. So see the 8.6 to figure out what factor will influence the type 2 error. And then we introduce some basic assumptions of the hypothesis testing and factors will influence the hypothesis testing. After that, we introduce what's the one-tailed hypothesis test and what's the difference between one-tailed hypothesis test and the two-tailed hypothesis test, right? And we introduce how to measure the effect size and how to measure the statistical power. Both of them can provide an estimation of the magnitude of the treatment effect. So that's the hypothesis testing. So we're going to do the homework of chapter 8, right, this week with the due date at next Tuesday, right? And next time we will introduce the t-test. It's similar, but I think we don't have time to introduce the t-test now. So if you have any question about this chapter, you can ask. So have a good night. I will still online for 10 minutes. If you have any question, you can ask. So bye, everybody.